Hello, everyone, and welcome to today's webinar on full survey chemical analysis of materials used in energy storage devices. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time. Dr. Rajiv Soman, Director of Purity Survey, will be answering some of the questions during the presentation. We will also collect these questions and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Dr. Xinwei Wang, Project Manager at EAG Laboratories.
Hello, everyone. Today's topic is full survey chemical analysis of materials used in energy storage devices. As you can see, there's two concepts we will be discussing today. One is about the material and their requirement for their usage in energy storage devices. And number two is that why we do full survey chemical analysis. Obviously, we need to know the composition of the materials, but on top of it, why we need to full survey? Well, one of the main reasons is that real material, they are not pure. So we need to understand what else in those materials, because those impurities, they may have a deleterious impact on the performance, on the energy density, on the cycle life, and the safety issues with regard to the batteries. So my name is Xinwei Wang, and I have 20 years experience in material science, engineering, and electrochemistry. My PhD actually focuses on organoelectrochemistries. And I joined EAG 12 years ago in third-party material testing services. And currently, my focus is on purity-related industrial applications using trace elemental analysis techniques and other gassing techniques. My focus is on technical consultation and project management related to those fields. So here, today's webinar will be organized, structured in a way that including 5 sections. Number one, we will give a brief introduction to Eurofins, EAG Laboratories, and overview what is past, present, and frontier in energy storage researches, including elemental and materials requirement for high energy storage devices, as well as spec limits. And then we will go over quickly the techniques used, including glow discharge mass spec and ICP OES-MS for the analysis of those materials. And then we will demonstrate a couple case studies that involves in the energy storage materials. Specifically, we will using lithium-ion battery as a case studies. Those include high purity graphite, which is an anode precursor, and high purity alpha alumina, which is ceramic coatings used for separators. And then we will talk about lithium transition metal oxides, which is cathode precursors, and the lithium lanthanum zirconium, which is an example of ceramic solid electrolytes. Then we will talk about discussing about the characterization of a next generation anode precursors with higher capacities. Those are silicon or silicon oxide doped carbon composites. And then we will go over or summarize what is a reference and guidelines in terms of analytical technical choice and their capabilities related to the production support for those materials. So who we are EAG, which is the European Material Science Division, and we have about 600 educated employees, and they are spread in more than 20 locations globally, and we serve about more than 4,000 clients globally in 50 countries. And here, those red dots and the blue dots are showing our locations globally. And the 3 particular sites I want to point out with arrows, those are our purity survey line laboratory, which can provide analytic services, in which circuit site is the center of excellences to drive all the method development and validation processes. Before we jump to others, I would like to go over a little bit our EAG's spectroscopy and the microscopy analytic resolution tools. This chart clearly shows the correlation of analytic spot size related to the information it gained, including the elemental information, molecular information, crystal structure information, and the surface morphology information, as is organized here. Today's topic will be specifically focusing on the technique for bulk composition analysis and the impurity analysis, including low discharge mass spec, which covers detection from percentage level to PPT levels, and the ICP OESMS technique in both solution and the solid sampling division, which covers, again, you can see from major composition level to the PPT levels. So before we jump into other side, we want to know where we are, where we come from, and where is the future or the frontier in energy storage researches. As you can see, the energy storage devices really started in the 18th century or 19th century, 2 centuries ago. And the material used over the time, you can see starting from commodity metals, copper, zinc, nickel, and lead acid to alkaline batteries until the 1990s, where the lithium ion batteries really starting entering the industrial production process. And today, they are the primary form of use, including the pouch and the prismatic cells. And this is where it is currently used in all the electric vehicles, and the majority used in the electric vehicles and the portable electronics and other consumer electronics. So where it goes, where is it heading? The future lies to the grid scale batteries, flexible electronics, and for body implants for nanoscale batteries. So one of the things you can see is from the beginning to the end, we are using more and more light elements. And on top of it, there are a couple of things we have to balance. Number one, of course, we are pursuing high energy density, but on top of it, there's other parameters need to be gauged, including the cycle life, including the reliability and the safeties, and of course, the cost. As you can see, in each application scenarios, the parameters, not all the parameters have the equal significance. Rather, we have to focus on weighing more on one or on others. And this is the future, and this is how what we see as energy storage material development. So what elements actually being used for high energy batteries currently, and where the future lies? Obviously, you can see, and those are the top of the periodic table are the ideal candidates. Those in the red, they are small, they have high volume charge density. Obviously, they are ideal for mobile charge as a mobile charger carriers. While those in the blue areas, including the carbon, silicon, sulfur, they provide the ideal anode material to host in the metallic form of their mobile chargers, while others like oxygen, fluorine, and then the transition metals create those lithium transition metal oxides of modified fluoride structure to provide the host structure for lithium ions in and out. And with that, this brings main functions. So you can see, you cannot just randomly throw those atoms together. You have to organize them in an orderly hierarchical structure for the device to function properly. For example, the cathode and anode, one of the way to structure them is to make the layer structure so that the lithium ions or other mobile chargers can in and out very quickly. And those oxides will provide also create a high electric potential so that open cell voltage can be high, that then we can have high energy densities. Aside from those elements must be proper structured, they also have to make sure there is nothing else in there. Otherwise, those things will also participating into the electrochemical process, and as a result, they can cause the performance deteriorations. So EAG has been working in this field for quite a long time. My colleague Linda Romano actually wrote an article regarding how to improve the performance and safety of lithium-ion batteries. And in that article, it is specifically discussing various techniques to characterize the materials and the interfaces. And for your interest, you may also click this link to look at the details of that article. But here today, our focus is more related to industrial production support of manufacturing processes. Specifically, we are looking into qualifying precursors used in the manufacturing lithium batteries. Certainly, we also do full battery analysis for failures. So we tear the batteries apart and analyze the individual components as you can see here. Primarily, our focus is on dealing with the manufacturing uncertainties that arises from the processing parameters, such as related to the coating thickness, the impurities, and more interesting, we are looking into qualifying the precursors and particularly the composition impurities. Here is materials we work with, the cathode, anode, ceramic coating, and for the future solid electrolyte ceramics. And here give you a more comprehensive ideas what we're working with, and we're working on the electrode side, ceramic coating side, and electrolytes, and the relevant spec requirement and the corresponding techniques for choice. Specifically, we will go over 4 case study of materials, including the lithium transition metal oxides, that including lithium cobalt, lithium LNCA, LNCM, and the graphite, and the modified graphite structure for next generation anode, and then ceramic electrolytes. So first, we wanted to go over a little bit of the GDMS and the ICP-OES-MS fundamentals. For details, we encourage you to go to the website to look at our GDMS webinar and the ICP-OES-MS webinars. For any analytical services or analytical method, two things we need to deal with. Number 1 is accuracy. Number 2 is precision. And this constructed 4 scenarios. On the top left, we are talking about a low precision and low accuracy, whether neither the measurement repeats itself or nor is have low bias. And then often you may also see a scenario where even the precision is bad, but accuracy, average accuracy is pretty good. And in most cases, we're dealing in a scenario where we have very good precisions, but not accurate. And the last scenario is everyone's targeting at, where the measurements are both accurate and precise. This is often achieved by through the established consensus value or reference from the reference materials. Then we get established bias and corrected accordingly. So regarding GDMS, ICP, OES, and MS, how they actually work. Okay, so for GDMS, it is a direct solid sampling technique. So obviously sample is a solid, and on top of that, a sample has to be actually, because it's ion beam sputtering technique, sample need to be conductive, electroconductive, or mainly electroconductive. So it allows a high energy argon ion beam to come into bombarding the sample and transfer the kinetic energy to the sample itself, causing the evaporation of atoms or secondary ions. The secondary ions are bring it back by negative bias voltage, so that allows a near exclusive generation of atoms. And those atoms then diffuse into the plasma, GD plasma, where it is infinitely diluted and ionized. With this mechanism, which means that the atomization ionization process separation in both time and space, they greatly reduce the matrix effect. With that, GDMS can do quantitative, semi-quantitative to quantitative analysis without strictly matrix matching standards. So how about ICP technique? How it is doing the analysis? Well, ICP is generally what we're talking about here is solution sampling. That means the sample is first converted to a liquid solution. That being said, the sample can be also directly sampled through the ETV process or laser ablation process. And once you have those liquid solution, for example, it goes through the nebulizer or spray chambers where it will be nebulized, forming micro aerosols. And this is a very uniform process, and you will get the proportion of aerosol entering the ICP torch or ICP plasma, where it is stripped of all the solvent, and the analyze is either getting energy and excited and releasing elemental specific photon emission, where it is detected by optical spectrometer, or the analytes are ionized and then extracted out through the mass analyzer, where it is separated and filtered to get mass specific signals. This is called, so we have both ICP OES and MS in places. So in EAG, we are a global leader in terms of purity survey analysis. We have 25 GDMS instruments. We have 7 ICP-MS instruments, 6 ICP-OES instruments that provides a solution and the ETV sampling process. And we have the technique 7 instrument to do hydrogen, carbon, sulfur, nitrogen, oxygen analysis. Those equipment and capacity is designed to make sure we can provide uninterrupted services for the industry. On top of the purity analysis, we also provide thermal microsampling analysis as well as sorption analysis. Those techniques are designed to do outgassing analysis or microanalysis with these two techniques. And with the increasing need for surface area characterization, we also provide sorption analysis. So here are a typical example of the direct solid sampling technique with all the GDMS model instrument we have. And we also have the one of the most sensitive ICP technique, the triple quad ICP-MS analysis technique. So that being said, now we were going over some of the case studies. And those case studies are structured in such a way that we will focus on the materials that have industry significance in the lithium-ion batteries. And certainly, there's a similar concept that can be applied to the other energy storage material like sodium battery or lithium sulfur, and also. And specifically, we will discussing the cathode precursor solid electrolyte, anode precursor aluminum coatings. After that, we will go over what are the specifications needed to make those high performance batteries. In terms of specifically, we'll focus on the composition side, the purity grade requirement, and the specific impurities that need to be controlled. And then with those insights, so what is the analytic challenges and what is the analytic solutions for that? What is the technical choice? What detection limits we need? What is the precision accuracy realistically can be achieved? So we're talking about a high purity graphite and a high purity alpha alumina. High purity graphite is commonly used for making the anode, and high purity alpha alumina nanoparticles are for ceramic coatings. Um, when we're talking about high purity, obviously we are talking about impurities. So why need to control the impurity? To what extent they need to be controlled? How they play the roles? Here shows you the effect of impurity on battery performance. So in one of the major impact is that it can catalyze in the formation of hydrogen or decomposition for electrolyte into gases byproduct. Here it shows you that the impurities can be, how they present on the graphite materials, and actually how once they catalyze out of gassing, what it looks like the battery will go through the stress mode. And you can see here, once those things happen, it can cause out of gassing, which is one of the major safety concerns for batteries. Aside from triggering the auto-gassing, impurities such as those metal impurities, they can actually by itself will, during the electrochemical cycle, they can create an electrical pathway that shorts the cell. Also, they can form internal microbattery causing self-discharging. And then there's also many other impacts that will remain to be investigated or discovered. So it is obviously there's importance of to understand the overall purity levels as well as specific impurity level and their distributions. Here is some example of the spec of a current production of graphite and then the future needs. Okay, here aside from ash and moisture content, there is a specific requirement for those pre-transition and post-transition metals. Many of them are magnetic impurities. You can see for the current production spec, most of them are tens of microgram levels, but for better ones, and the current industry is actually pushing for control of the magnetic impurities, the four of them to total less than 0.1 microgram per gram or 0.1 ppm. So this obviously it will create a strong demand on the analytical capability of current techniques. So aside from graphite, actually for alpha alumina nanoparticles used for ceramic coating, the requirement, the purity requirement is even higher. It requires 99.995 to 59 purities. So how do we do that? Well, here we want to go over a couple of tracer analysis technique with you. Obviously, ICP-MS is one of the mainstream technique and is an industry standard technique for many, and then tracer analysis. And then GDMS and ETV ICP-MS. We want to go over this in terms of two categories of criteria. Like any other things, we need to have a criteria when we're judging something, and then we can correspondingly make decisions with it. So in terms for production support, not only we need the attributes of the analytic technique itself, but how they actually being able to support the industry production process. So in terms of the analytic attributes itself, you can see ICP-M has a lot of wonderful characters. It has a flexible sampling size up to gram level. Its NIST traceability is fully quantitative. It has excellent metal coverage, including metals, metalloids, and non-metals. And the detection limit actually depends on the sampling size and the instrument they use. It can be PPT levels and above. And but there are certain issues with regarding to the industrial production support capabilities, because you really have a very good control of the individual app to control the contaminations. The process involves extensive sample preparations, and so the turnaround time it will be delayed, and the cost of analysis because it involves a lot of consumables. That being said, so actually with all those advantages, we want to know are they applicable to high purity graphite and alpha alumina? Not exactly. Those things doesn't digest easily. So all those wonderful features of ICP-MS cannot be realized because we cannot digest them, or very difficult to digest them to maintain the long-term reproducibilities for this particularly high purity graphite and alpha alumina. So that forces us to look into the options of solid sampling technique, let's say glow discharge mass spec and ETV. ETV is another emerging technique that people have been excited about. It has a lot of similar features as ICP-M as it is quantitative. It has similar elemental coverage and detection limit, low detection limit for many elements. And it's possible to certify 49-59 purity based on the limited set of elements. But there are also challenges. And the challenge is as calibration is not so easily achieved, and it's not a really a continuous mode of like ICP-MS or ICP-OES. So the precision suffers, and there's a lot of questions on how to liberate the analyze and make sure the transmission of the analyze into the detector is in full 100% levels or good recovery levels. And because it's basically a batch mode, the turnaround time is slow, and the throughput is not ideal. So this leave us, GDMS is really a natural choice for analyzing high purity graphite and alumina. It has all those great advantages, being with direct solid sampling and good elemental coverage and excellent detection limits. More importantly, it has long-term reproducibility and high throughput. And the cost of analysis, for industry, it has to be realistically low so that they can afford. In terms of elemental coverage, traceability-wise, it depends on the elements. Some of them are qualitative, some of them are semi-quantitative, and some of them will be quantitative. So, but one of the most important things is that you will not missing any elements. If it is there, you will find it, and it's just a matter of time, a matter of judgment how to make it more quantitative. While other technical, you will always can raise the doubt whether I actually detected them, or if I detect them, whether I actually introducing contaminations. Well, in the GDMS, those kind of doubts can be cleared very quickly. So as we see, well, one of the primary concern in the high purity graphite, high purity alumina analysis is to see how clean your feedstock is. For GDM analysis, there are two ways to sampling. One is coaxial sampling, where the sample is shaped into a pin of 2 millimeter by 2 millimeter, 20 millimeters. And also, certainly you can do in the flat sampling geometry, whether if you have powder or granules, you can put them on the 7-9 impurity binders. Southern powders can also be done with a tantalum spoon in a pin geometry. So those are the typical features of GDMS analysis in this modes. You can see it has full periodic coverage and excellent detection limits. And the sample is good in the liquid nitrogen. Why so? Because it makes sure the impurity doesn't redistribute during the analysis. In the plasma process, it can be high temperature, so this makes sure there is no temperature gradient driven segregation behaviors. Here, example on analyzing graphite blocks with GDMS. This is a typical sampling size is 8 mm diameters, and this is the crater shape, crater morphology of the analysis. This is actually the crater size. You can see it has 8 mm diameter and a depth of about approximately 20 millimeters, 20 micrometers. So it has a pretty large representative sampling volume. More importantly, we want to point out is that matrix signal is really high. It's 49 counts per second. With that, they give us the ability to sensitively detecting the trace elements. One of the important requirement for trace analysis with mass spec is to resolve the mass interference. In the plasma conditions, not only the analyzed isotope will be shown up, but many polyatomic interference, whether from the matrix or from the charging gas, for example, argon, they can form various polyatomic interference. For example, some of the key metal impurities in carbon will show up let's say for the titanium 48, chrome, vanadium, iron, and nickel, you can see they all have mass interference, which has very, very similar masses. But with our high resolution mass spec, we can easily resolve them, and that gave us the ability to accurately quantify those elements. Here is showing you the reporting limits of the GDMS analysis of graphite. You can see it has the ability to scan all the elements in the periodic table from lithium all the way to uranium with a detailed reporting limit at 0.01 to 0.1 ppm. With such a low detection limit, it gave us the ability to analyzing 5.9 to 6.9 periodic graphite. Here is we're trying to assess how accurate the analysis results is. So we're using BAM standard SS09. It is a graphite based reference materials. And first you can see that it has those elements that are relevant to the energy storage of materials, those pre-transition metals and transition metals, and they have the relevant certified values. And you can see the GDMS results, whether it's in this DC mode or pulse mode, the value are strikingly good. Their variation is only within a factor of 2 or 3 most scenarios. One thing we want you to know that for trace analysis, only when this impurity level are jumping by order of magnitude, we will consider that as statistically significant different. Otherwise, you can see for solid samples, the impurity distribution are generally wider than in the solution mode. Why is the reason? Well, graphite, here is a graphite material. They have layered structure. Over time, the purification, you can see those rough, flatter layered structure become more regular and layered very well. And you can imagine the impurity trapped there, they not necessarily will be homogeneously distributed to begin with. Worse is that many of the impurities, even when they are started with oxides, they will react with carbon. Some of them will be reduced to metallic form. Some of them actually forming carbides. Those all will add to the heterogeneity of the impurity in graphite. Regardless, we have been using GDMS to do the high purity graphite analysis. Here is an example to show you how excellent long-term precision we can reproducibility we can achieve. Here it shows you the purified graphite from produced from 1994 to 2003, which is a decade samples, and we want to monitoring the boron, which is trace levels. You can see out of the each side of the 210 lots at the average about 0.3 ppm levels, we achieve very good precision. Likewise for this set is also. So this clearly demonstrates that GDMS is very effective for long-term monitoring of critical trace impurity in purified graphite. And now what about the aluminum or the other non-conductive oxide? As we mentioned earlier, GDMS is an ion beam sputtering technique, which means the sample needs to be conductive or made conductive through the use of secondary electrode. In terms of analyzing aluminum powders, so we typically will use a tantalum electrode, but we can also using other high purity metal electrode as well, such as indium or copper. And the sample is typically pressed on on this pin, tantalum pin, and being analyzed. For details, we also encourage you guys to refer to the one of the Astrum application notes that we also contributed, which is chemical purity determination of advanced alumina samples by Astrum glow discharge mass spec. Just let you know, we have multiple Astrum in-house to support the alumina analysis. Here, of course, like other technique, we all want to verify how good the GTM analysis to the high purity alumina. Here are the two reference material we worked with. Again, you can see the transition, the metals or impurities are relevant to energy storage are covered with certified concentrations. We have two reference material with different concentration range. And you look at, we evaluate in actually three different with three different electrode materials: tantalum, indium binder, and the copper holders. In most scenarios, we have reasonably good agreement with it, with the variation typically is a factor of 2 or 3 or so. And like the graphite, the impurity in the oxides typically will experience increased variation because the impurity not necessarily dissolved in the ceramic, rather they could be forming as inclusions or so. This is on will need naturally increased variation of the distributions. So again, let's look at the reporting limits. You can clearly see that again, GDMS has ability to cover the entire periodic table from lithium all the way to uranium for the alpha alumina analysis. And most elements will have a reporting limits 0.05 to 0.1 ppm. So it can easily certify 5-9 purity alpha alumina that are used for the necessary for the battery industries. So second, we wanted to discuss about the cathode material precursors. Specifically, we want to talk about lithium transition metal oxides and the lithium lanthanum zirconium as example for ceramic solid electrolytes. So what is the spec requirement? Give example, let's say we're talking about lithium cobalt oxide, which is the initial development for the lithium ion batteries. And you can see one of the major things, not only you need the impurities, but you actually also need to precisely what is the metal content of the cobalt, lithium, and specifically more than lithium cobalt ratios, because their ratios can have impact on the cycle performance and the stability of the lithium transition metal structures. So because let's go with a couple of techniques we can go over for the XIF and EDS. Both techniques cannot detect lithium, so that's out. ICP-OES can detect lithium. In our standard operation mode, the major contribution to the measurement error or measurement uncertainty is lithium easy ionization effect and the instrument drift. With that, the expanded measurement uncertainty is typically 3 to 5% at a 95% confidence level. Obviously, that's not enough to allow us to do accurate lithium transition metal content ratio control. So that's then we have to think about how do we actually correct those effects. In EAG, we follow the NIST high performance method or the high HP ICP-OES method. We control those effects, correcting those effects. With that, we can do achieve expanded measurement and uncertainty less than 1% at 95% confidence level. This allows us to do precise measurement of the lithium transition metal ratios. With that, we can effectively evaluating the deficiency or excess of lithium in the lithium transition metal oxide precursors. And for that, we have also developed white notes papers regarding high performance ICP-OES technique for analyzing complex oxides. So how do we do it? How do we do high performance? How do we actually correct in the measurement errors? So we need to know where their major sources. Here is a breakdown of the measurement errors from the standard ICP-OES. You can see instrument drift and the volumetric measurement are the major source of error. So in our NIST high performance mode, those effects are taken care or corrected. Without that, we can achieve uncertainty less than 1% and 95% confidence levels. So here is an example how the instrument drift can be in the ICP-OES technique. And that's why it is important to correct this drift. And with that, we can look at the actually estimated uncertainties from each major contributors. That's the reference material itself, sample itself, and the certified reference materials itself. With that, you can see the combined uncertainty, we can choose 0.21. When we do statistic expansion, so the expanded uncertainty is only 0.45 relative. So with this technique, we can accurately and precisely measuring the lithium content as well as other metal content in the lithium transition metal oxides. And this allows us to accurately assessing the deficiency as well as the excess of lithium in those materials. Aside from the composition elements, obviously we need to know the the impurities as well. Well, now those materials, the lithium transition metal oxides such as lithium cobalt oxide, they're soluble. So suddenly it opens the door for the ICP-MS or OES analysis. And all the advantage of ICP-OES-MS can be achieved, for example, is fully quantitative. That being said, it doesn't come without a limitation. For example, you need to do high dilution. And the lithium is notorious for its memory effect in the ICP technique. And because the solution technique, generally you don't include chlorine or sulfur at a very high detection limits. And the long-term reproducibility, it really depends on individual lab's ability. In UAG, we do have a lot of digestion tool. We have skillful staff that can efficiently do those things to control the contaminations. Certainly it can be done with ICP-MS OES, but it also can be done with the GDMS technique because those advantages we talk about, specifically it has the ability to including chlorine and sulfur. While in the ICP, we have to rely on the more like IC technique to do that. And it has excellent long-term reproducibility. Now, what about solid electrolyte? I'll give you an example, the lithium, lanthanum, zirconium oxide. You can see digesting them is not going to be so easy. To digest, to break down the zirconium matrix, we need to using HF typically. And once you're using HF, what happens? Well, HF is known to precipitate rare earths pretty easily as a rare earth oxide fluoride. For example, lanthanum is particularly has extremely low solubility product, so any addition of fluorine has to be very carefully controlled, otherwise you will cause the entire lanthanum precipitated out. As such that it is a very cumbersome process to do impurity analysis with the ICP technique for those materials. Rather, GDMS will be our natural choice. So that being said, in this regard, the lithium transition metal oxides is a matter of choice of each lab, whether it can do ICP, OES, MS, or do GDMS. Well, on the solid electrolyte, we encourage it. We'll choose GDMS over the solution sampling technique simply because of the challenges in the dilution, the dissolution process. Here is an example how the impurity analysis is important, why it is important. Here's an example of GDMS. You see we have suppliers from A to H for the analysis of lithium iron phosphate. You can see even though the major composition is lithium or iron phosphate, the impurities varies from vendors to vendors. And one beautiful thing about GDMS is that if something is there, you will not miss it, even at the very low levels. Likewise, on those other impurities relevant, you can see even though a material, just by looking at its name, we said, oh, this is lithium iron phosphate, but there's a lot of things behind all those impurities. It depends on the precursors you use, the raw material, your processing equipment, and how do you do sampling and the packaging. So all those things will contribute to the final performance, consistency of the batteries assembled. Here's a quick summary of how to characterizing cathode material as a solid electrolyte in terms of the key spec requirement, the analytical choices, and the key performance criteria. Now we wanted to come to the analyzing of the next generation or anode material. This is silicon or silicon oxide doped carbon composites. Those are used for anode as an anode precursor to improve the capacity. And usually those materials are not used in 100%, or rather the silicon used in 10% or so. so that you can manage the thermal expansion or stability during the cycle. So there are a couple of things we need to do. For those materials, we need to accurately measuring the carbon content, accurately measure the silicon content as well as oxygen, because oxygen loves carbon, oxygen loves silicon, and they are naturally getting in, and they will affect the performance. So for carbon content, typically we will using combustion IR. In EAG laboratory, we can, with our high performance mode, we can achieve ISD less than 0.5% relative. In terms of silicon, we developed the way to stabilize silicon in the solution, and we can achieving relative measurement uncertainty of 3 to 5% at 95% confidence levels. And for oxygen, we also in EAG we have being able to develop those methods that can achieving ISD 5 to 10% at 10 to 100 ppm levels, or 1 to 5% even at high oxygen levels. So for the composition, this is typically what we're using. And what about the impurities? The impurities are similar to those in the graphite in terms of their requirement, but here it differs because these two-phase structures. Now, when we run GDMS, we have to assume they are homogeneous phase structure, so that the internal standardization process can be carried out. But because this is two-phase structures, it increases the heterogeneity and increases the error in terms of quantification. But here, GDMS actually play good roles. With a modified semi-PV49 method, we will be able to validate the method and use it for trace impurity analysis, particularly those elements, achieving detection at sub-ppm levels with the sampling size 0.1 to 1 gram. So here's a little bit more because regarding the modified PU semi-PV49 method. Semi-PV49 is actually the testing method for the measurement of elemental impurities in silicon feedstocks for silicon solar cells. And it using the bulk digestion method with the inductive ICP-MS to do the quantification. It covers those elements, including alkaline elements, alkaline earths, and first-series transition metals, such as and many of the also even the post-transition metals as well. So in EAG, we did our own method validations, and for those, for example, those specific elements, we have done the linearity check, the detection limits, determination, precision, accuracy, and dynamic range. Here it shows, and it gives a very reasonable, meet our performance criteria, acceptance criteria. With that, we have been using it to serve the industry. Here is a summary. So as reference and a guide for chemical analysis of lithium-ion battery material, certainly the similar principle can be applied to other energy storage materials. For anode precursors, the analysis, particularly graphite and silicon or silicon oxide doped carbons. For purity-wise, GDMS is good for graphite, and it provides ppb to 100 ppb levels. And for silicon doped carbons, silicon content is typically analyzing by ICP-OES, while for the transition matter impurities, ICP-M is a natural choice. And in terms of silicon oxide doped, it is similar, but also we needed to accurately measure the oxygen content in this material, because if it is, particularly we're actually using the fraction mode to separate those, in the amorphous silicon oxide, or those actually in the crystalline silicon oxide. If it's crystalline, it will create a barrier for lithium actually diffusion through it. So it is important that you can not only measuring the total oxygen content, but also actually how the oxygen is bonded to silicon and how it's bonded to our carbon. And then in terms of the composition analysis, here we show you the measurement uncertainty. So when you get a number, you don't see as the exact number, you actually know the range. And because that's realistically all the analytical technique will carry a uncertainty, and it's a matter of time. It's important that you know how wide that uncertainty is. So for the lithium transition metal oxides and lithium lanthanum zirconium oxide, you can see we recommend using high performance ICP-OES, and the sample size can be pretty big, so it is very representative, and we can achieve measurement uncertainty less than 1% at 95% confidence levels. For those we can certainly try high performance, but the cost concerns, normally we will recommend just standard ICP OES. With regard to carbon, we can do combustion ion in a high performance mode to achieve less than 1% or less than 0.5% uncertainty. So, and here it shows you the sampling size. Overall, we are talking about hundreds of milligram levels, and that's generally can guarantee the representative sampling process. And in terms of the trace analysis, here is a summary of the examples, for the relevant precursors and the detection limits it can be achieved, and which technique should be used. For graphite alumina, lithium transition metals, or lithium lanthanum zirconium oxide, you can see with GDMS we can easily achieve sub ppm level detection. With those, obviously ICP-MS is a natural choice. You can see we also in EAG we can achieve greater detection limits and reporting limits. That being said, if you have a requirement for lower reporting limits, we can do it. We will modify the method and to do that. Those are just represents our typical reporting limits. Okay, so why choose EAG? The EAG has many value propositions, and here is some of them. And we are, ISO credit companies. We have a lot of instrument capacities. We actually usually take a multidisciplinary approaches. On top of it, in light of the pandemic that's offering us, or right now, I wanted to stress that EAG Laboratory is committed to the safety of our staff and clients. Worldwide, we have compiled with the latest COVID-19 regulations from state and the local governments, as well as the Center for Disease Control. Currently, all of our locations throughout the world remain open, but we may have limitation on customer visits, as this is a fluid situation where we are operating laboratory at a reduced capacity. We can also transfer your sample to another EAG locations. We encourage you to discuss your options with our sales representatives.